Hello all. Now let us continue with the further part of real sequences. Last time we talked about the operations on convergent sequences, then operations on divergent sequences. As far as convergent sequences are concerned, they go along with the usual algebra that we apply. Meaning, sum of two convergent sequences is convergent and converges to the sum of the limits. Sum of a convergent sequence with a constant sequence also converges. Difference of convergent sequences also converges. If we multiply two sequences term-wise, which are convergent, that also converges to the product of the limits. Even we have seen the quotient also converges to the quotient provided the denominator is non-zero. In case of divergent sequences, we have seen if both the sequences are divergent, then their sum will diverge to infinity. If one sequence is divergent and the other is bounded, still their sum will go to plus infinity. I mean, it will diverge. So these are the cases that we dealt with in case of divergent sequences. Now let us go a little bit ahead with some new concepts. That mean limit inferior and limit superior of a sequence. You can see, if you are given any sequence Sn which is bounded above, then we know that if suppose I am handling a sequence Sn and from 1 to infinity, and we know that it is a bounded sequence, which will mean Sn is less or equal some capital M, and this is true for all natural numbers. I mean, for all n belonging to I, means right from the first term, S1 is less than M, S2 is less than M, likewise. So all the terms are smaller than some fixed value M, then we know that it is bounded above. So what we are going to do is, term wise we are going to define their upper bound, least upper bound. So let us go on dealing with terms. Suppose I am talking about S1, S2, meaning the whole sequence, S3, and so on. If I handle all the terms and find out its supremum, if I find out its supremum means least upper bound of the set, we will call it as capital M, but because we have started from the first term, we will denote it as M1. Then we'll go with M2. How will be M2? M2 will be LUB, least upper bound, means supremum of the set starting from S2 onwards. S2, S3, and so on. Then we'll go for M3. M3 will be the least upper bound of the set S3, S4, and so on. So in general, we will call this as Mn. We'll call this as Mn. Mn is the least upper bound of the set that starts with nth term Sn, Sn plus 1, and so on. So what we observe, what is LUB basically? What is least upper bound? That we must come back to the concept. So let us go back again to the earlier versions. See, if you are given any set S, then all the elements X belonging to S, if they are all less than U, some small value U, some real number U, or at the most equal, equality is allowed. So this U is some fixed real number for which every member of this set is smaller than U, then we call U as upper bound. Upper bound. And amongst all the upper bounds, we find the smallest of all, that is known as least upper bound. Smallest of all the upper bounds we call as least upper bound. Means what? What is the least upper bound? It is basically itself an upper bound. And second thing, what it talks about, no number smaller than no number smaller than so which number we are labeling as LUB? Suppose M. So no number smaller than M is an upper bound. Is an upper bound. So these two conditions are very important for us. Upper bound, it should be an upper bound. By upper bound, what we mean? Every element of the set will be smaller than or at the most equal to this M. And when it will be the least of all the upper bounds, if no number smaller than M is an upper bound. So M is the smallest of all. If it happens, then we say that M is the least upper bound. So seeing this concept, let us go back here. Originally we had the whole set. Then we excluded S1, we have the set from S2, S3 and so on. Then we excluded S2 also, and we are moving back to S3, S4 and so on. So in this way, every time we are deleting the nth, the previous entry, and we go ahead. So what will happen to this supremums, least upper bounds? Because we have deleted 1, 1. So what will happen? M1 will be certainly greater or at the most equal to M2. Because what? We have taken the largest of all out. Largest term we have taken out. So naturally, the next term onwards, it will be smaller. Then M3 will also be smaller than that. And so on. So what do we get? We are getting a decreasing pattern, monotone decreasing sequence. So in general, what I'll say, if I want to say in general, what should I say? N plus 1 the term, M n plus 1 must be smaller than Mn. N plus 1 the term must be smaller than Mn. So this is the trend that you are following. So you get a monotone sequence over here. So let us once again see to this theoretically. So what we are saying, Mn is the LUB of Sn, Sn plus 1 and so on. So Mn will be greater or equal Mn plus 1. So we get the sequence Mn as a non-increasing. Non-increasing means decreasing sequence, and a decreasing sequence, if it is bounded below, it will converge, and if it is not bounded below, it will diverge to minus infinity. And that is why I just enlarged this to give you the definition. So what the definition says, if Sn is a sequence of real numbers that is bounded above, and Mn equal to the LUB supremum of the set starting from Sn, Sn plus 1, Sn plus 2 and so on, then we have to see that this singleton Mn, I mean the set Mn, the sequence Mn is a monotone sequence. Now monotone sequence, if it converges, then its limit will be called as lim sup, means limit superior of the sequence. And if it diverges, then limit superior is defined to be minus infinity in this case, because it is going down, it is reducing. Let us deal with this particular example, that will make it more clear. You can see the example of minus 1 raised to n. Minus 1 raised to n is a bounded sequence, we know. It lies between minus 1 to plus 1. So let us have this as an example. Manually let us write it over here. See, this sequence is minus 1 raised to n, meaning first term is minus 1, second term is plus 1, third term is minus 1, fourth term is plus 1, next is minus 1, next is plus 1, and so on. So what you observe, if I take M1, it will be certainly 1, supremum is 1. If I go with M2, still it will be 1. If I go for M3, still it will be 1. So what we observe, this is a constant sequence, and constant sequence will converge to the constant value 1. This is what we mean over here. I suppose the thing is quite clear. In this case, the sequence is in this case the sequence is bounded above, and it converges to the same limit. So limit of Mn is 1, and limit superior is also 1. Now they have given another sequence, 1 minus 1, 1 minus 2, 1 minus 3, likewise. So let us deal with this. So now let us handle another sequence, S equal to, it is 1 comma minus 1 comma 1 comma minus 2 comma 1 comma minus 3 comma 1 comma and so on. What do we observe? This is our first term, second term, third term, fourth term, fifth term, sixth term, and so on. How would you define this sequence? Sn. Yes, we should be able to define the sequence. First term is 1, third term is 1, fifth term is 1, seventh term is 1. Means the value becomes 1 if n is odd. And what about this term? This is second term, value is minus 1. Fourth term value is minus 2. Sixth term value is minus 3. Eighth term will be minus 4. So if n is even, we find value is half of it but negated. So value is minus n by 2. Value is minus n by 2. So this is the sequence we have to take care of. Alright, so let us go on seeing what are the superiors, limit superiors. So what will be m1 in this case? m1 means right from the first term onwards. m1 will be, so from first term onwards, what is the greatest of all? Limit superior. So 1 is the limit superior. What will be m2? From minus 1 onwards, still 1 is the limit superior. For third, still 1 is the limit sup, because all are negative terms, so this becomes constant 1. So this is fixed. m1, m2, m3, they are fixed values 1, no doubt. So limit superior of this sequence is 1. So in this case also limit superior is 1. Now let us handle another sequence. I hope in this case I would like to note it over here. I would like to note it. Just a minute. So what we got? Lim sup of Sn. Sn goes to infinity is the same as limit n tends to infinity of this mn, and what we are finding here, mn remains the same, though the terms, alternating terms, they are varying. In the upper case all the terms were actually oscillating between two values, but this you can see oscillates infinitely. So this value still is 1. So we dealt with two examples, the upper being the constant one, and the lower actually oscillating infinitely, still both are having lim sup as 1. Limit superiors are fixed values ones. Now let us deal with another example, that which is not bounded below. So S, let us talk about minus 1, minus 2, minus 3, minus 4, and so on. How is the sequence? Sn is equal to, so I would like to pose this as a question to you. I would like to go with a poll. If capital S equal to curly bracket minus 1 comma minus 2 comma minus 3 comma minus 4 comma dot dot dot, then Sn equal to dash. option is minus n, option is n minus 1, option is 1 minus n, and last option is minus n minus 1. So you are very right, and the sequence talks about the terms minus n, negative of n. So let us take the thing over here, Sn is minus n. Alright, then now let us go with what will be m1. m1 means supremum of all this, so it is clear cut minus 1. If I go to m2, what is the supremum? Obviously minus 2. Supremum starting from third term onwards is minus 3. So the terms sequentially come out as the supremums of the sets, corresponding sets. So what this will mean, what will be the limb sup? We find the sequence is decreasing, no doubt, but it is not bounded below. So if it is not bounded below, the limit superior will go to minus infinity. So limit superior is minus infinity. Okay, in this case limit superior is minus infinity. Hope the scene is quite clear. Let us once again read the definition aloud. What the definition says: if Sn is the sequence of real numbers that is bounded above, and Mn is the supremum of the set starting from Sn onwards, if this sequence Mn converges, then the limit superior of Sn will be the limit of Mn, sequence Mn. And if this sequence Mn diverges to minus infinity, then the limit superior is defined as minus infinity. This is the case when the sequence is a bounded sequence. Now, if the sequence is not bounded above, then there is no question at all. The limit superior is plus infinity. If it is not bounded above, the terms will go on increasing in that case. So naturally, the limit superior will be infinity. So one more point let us concentrate to. If the sequence Sn is bounded above and has a subsequence that is bounded below by A, then the limit superior will always be greater than or equal to that particular a. So this is for the bounded sequences. So here itself you can verify it. Here itself you can verify. If I talk about the first sequence, minus 1 raised to n, terms are minus 1 1, minus 1 1, minus 1 1, likewise. We see that the sequence is bounded above by 1. So in this upper case, what we find, all the terms Sn are less than or equal to 1. Now if I consider the subset, a convergent subsequence I can call minus 1, minus 1, minus 1, and so on. The supremum of this particular is minus 1 only. Supremum is minus 1 only, and in this case limit superior we have defined 1, we have seen already. So this minus 1 the value minus 1 the value minus 1 is smaller than this value 1. In rare cases they will be equal, but in this case it is strictly less. Minus 1 is strictly less than 1. So what we have seen, if Sn is a sequence that is bounded above and as a subsequence that is bounded below by A, then this limit superior will be always greater than or equal to A. And second thing, if Sn has no subsequence that is bounded below, then limit superior will be minus infinity. So these are the two things we have to take care of. One example is given over here. If we handle a sequence like 10 raised to 100, comma 1, comma minus 1, comma 1, comma minus 1, and so on, still its limit superior is going to be 1. How? How the limit superior is going to be? Let us take this case also. What are the terms of our sequence? I would like to change the color. Okay. See, just a minute, let me increase the size. See, our sequence S contains 10 raised to 100 or 2 bigger term, 10 raised to 100. Next comes as 1. Next comes as minus 1. Then again 1. Then minus 1. And so on. Let us try to write the values of m. What will be m1 in the first case? No doubt 10 raised to 100 is the biggest value, so that this will be the limit superior, supremum. m2, if I go to, certainly this value is 1. m3, if I go to, what we have done, we have started with third term onwards, from minus 1 onwards. So in this case also I'll find m3 to be plus 1 and so on. So though I have this term over here, I find the next terms, actually the sequence is a bounded sequence in this case. So what will be the limit superior? It will be 1. What will be the limit superior? It will be 1, because limit superior, how do we define it? If the sequence is a convergent sequence, then its limit is the limit superior. So this sequence is bounded below by 1. So the limit superior has to be 1. Now I'd like to proceed with this particular theorem. What does this theorem say? Okay. If Sn is a convergent sequence of real numbers, then limit superior Sn is the same as limit of Sn. Means the limit of a convergent sequence itself is the limit superior of that sequence. This we mean to say. So let us try to prove it. Let us try to prove it. See, we say L is the limit of the sequence. When do we say L is the limit of the sequence? If the terms Sn are close to L, not all, but infinitely many. So close to L meaning smaller than epsilon. The difference is smaller than epsilon for all n after certain fixed natural number capital N. So this is what we mean by the convergent sequence, and limit is L. Now this statement itself means that this Sn minus L lies between minus epsilon to plus epsilon. Writing this is itself the statement. Writing Sn minus L lies between minus epsilon to plus epsilon itself means that absolute value of Sn minus L is smaller than epsilon. This is what we have. Now let us add L throughout so that we will be talking only about Sn. So if I add L throughout, what do I get? L minus epsilon less than Sn less than L plus epsilon. But when? Not for all n. This is only for n's crossing this n. After this n only. So what this means, if all Sn lie between L minus epsilon to L plus epsilon, actually let us recall, we used to call Mn M suffix n. What is Mn? Mn is the least upper bound of what? The terms after Sn. Sn plus 1, Sn plus 2, and so on. What we mean? For all n greater or equal this capital N. I'm sorry, I should replace this by capital N. I'm sorry. I should write here capital N. No, that will mean only for capital N. I'm writing for all n's. I was right. I was right. So let us replace it. This is Mn and this is Sn here. Yes. And let us write, this is for all n greater than or equal to capital N. All these Mn will lie between L minus epsilon to L plus epsilon. L minus epsilon less than Mn less than L plus epsilon. I hope the thing is quite clear. If the terms are themselves between these two values, then the lim subs will also be, I mean the limit supremums of these things will also lie between L minus epsilon to L plus epsilon, and very naturally we are getting the same kind of condition over here. So what we can say, mn minus epsilon mod complete less than sorry, extremely sorry. Here I should have L. Mn minus L is less than epsilon for all n belonging to n. So I have highlighted the value L, and I have highlighted that the difference is smaller than epsilon. So what this will mean particularly for us? This means that limit as n tends to infinity of this sequence Mn is L, but the limit of Mn is, in our language, limit superior. Of Sn. So we have shown that the limit superior of Sn is the same as the limit of Mn. So limit superior itself is the limit of Sn. Limit of Mn is itself limit of Sn here that we have taken. But when it happens, if the sequence is itself convergent, then only it will have its own limit. I'm sorry. Now up till now we were talking only about the limit superiors. Now we have to talk about the limit inferior. So the same thing that we talked about for supremum, same way we will be talking about infimum. It's but natural that the sequence must be bounded below. If the sequence of real numbers is bounded below, then we will be talking about its greatest lower bound, and again we will define on the same lines. So this being a dual concept, I think I should not much explain it. I'm sorry. See, if the sequence of real numbers Sn is bounded below, then the set Sn, Sn plus 1, Sn plus 2 and so on has a greatest lower bound, means infimum, and that infimum we are denoting as small m suffix n. If the sequence of Mn is non-decreasing sequence, this is a non-decreasing sequence, it will go on increasing, and hence either it converges or diverges to infinity. The things are quite dual things. Whatever we did for superior, same kind of things we are going with inferior. So we know very well the lower bound is Mn, and for the next set Sn plus 1, Sn plus 2 and so on, it will be Mn plus 1. So both being lower bounds, the earlier lower bound has to be smaller than the next lower bound. That is the concept. So what happens? This is a non-decreasing sequence, so it becomes increasing one. So in the same we can see in the same cases, same examples if we handle. Let us handle the same examples as we did already. So the sequence of minus 1 minus 1, likewise okay, we have to take it separately. All right, I'll be taking it. All right, so if suppose we are having a set, so I would like to go with the poll. If capital S equal to curly bracket 1 comma minus 1 comma 1 comma minus 1 comma dot dot dot, then lim inf limit inferior of S equal to 1 or minus 1, what it will be? So I end this poll and let us see what has happened. You have set s equal to 1 minus 1 1 minus 1 1 minus 1 and so on. If you talk about small m1, small m1 means infimum. Infimum means lower bound, least, I mean greatest to lower bound. So infimum of this set 1 comma minus 1 comma 1 comma minus 1 and so on. So what is the smallest value? It is minus 1. If you go with m2, we are talking about infimum of first value is not taken, first term is not taken. We start from second term, minus 1 1 minus 1 1 and so on. Still what we find? Infimum is minus 1, the smallest value is minus 1. So every time small m1, small m2, small m3, all of them they are minus 1. So in general, if I talk about mn, this will also be minus 1. You find it's a constant sequence of mn, sequence of mn from 1 to infinity. This is a constant sequence with terms minus 1, minus 1, minus 1 and so on. So it will converge to what? Minus 1 only. And if it converges to minus 1, what will be its limit? Limit is minus 1. So naturally, limit inferior. We call this as limit. I said it's a dual concept. Dual concept. So limit inferior will be minus 1. For the same sequence, we have already seen that limit inferior, limit superior, we have already seen. It happens to be plus 1. Why? Because we were taking supremums. In this case, we are taking infimums. The second example that we handled was, let us deal with it. Second example was s equal to 1 minus 1 1 minus 2 1 minus 3 1 minus 4 and so on. Is this sequence bounded below? Obviously not. The sequence is not bounded below. Let us have two parts of it. Already we have seen the limit supremum, limit superior. So we were handling supremums of this. So what was m1? Supremum was 1. m2 supremum was 1. m3 supremum was 1 and so on. The supremums formed a constant sequence. Now what happens to the infimums? If I go with small m1, what is the infimum? What is the smallest value? So this set is not bounded below as you are watching. So m1 will go to minus infinity. What about m2? It will go to minus infinity. And in case of minus infinity, it will be a kind of daring to write equal to. I have written equal to. So that is a kind of daring. You cannot catch that value. You cannot write that value equal to something. So very directly, what we mean to say, limit inferior. limit inferior as n tends to infinity of this sequence will go to certainly minus infinity. Why? Because it is not bounded below. So if limit inferior exists, then that sequence must be bounded below. Same is the case with limit superiors. The sequence must be bounded above. Then and then only we can find out the limit superior and limit inferior. Now let us go on handling the sequence s equal to same that we handled earlier, -1, -2, -3 and so on. So this sequence is also not bounded below. Though it is bounded above, it is not bounded below. So what happens is limit inferior in this case is also minus infinity. So limit inferior limit inferior of s is minus infinity in this case. Now if I go with another sequence, suppose we go with s equal to, let us take all these terms positive, 1, 2, 3 and so on. Then what is going to happen? What will be small m1? Small m1 is the greatest lower bound, it is 1. If I start with second term, what is it? 2. If I start with third term, GLB and so on. You see, it's an increasing sequence, but it is not bounded above. So very naturally, limit inferior of this sequence S. What is it? Is it converging? No, it doesn't converge. It is not converging. So the value goes to infinity. In this case, I'm extremely sorry. M1 is the infimum. Yes, it's right. So I would like to stop for this moment. I'll continue the same part again. Bye then.